right, there we are. All right, so third order linear differential equation with constant coefficients. Boom, 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 lots of adjectives. Whatever the order of your equation is, so if you have an nth order differential equation, you either have no initial conditions or you have n initial conditions. So an nth order DE would have n initial conditions. Probably. It would be a weird situation if you had less. At most n initial conditions for sure. So here I've got a third order, I've got 3 initial conditions. I know something about initial position. If this is position, this is velocity, this is my acceleration. What's the third derivative, physics folk? What is the third derivative called? Those are like second derivative is acceleration. What's the third? What is the rate of change of acceleration? Anybody know what that's called? I think it's called jerk.
Yes.
Yeah, so like it's like the suddenness of the acceleration. So we don't have that here, but it's involved in the equation itself. But we don't need to have any interpretation. Because we know what we're going to first do is get the characteristic polynomial. And that's easy. I'm going to take lambda and replace derivatives with powers. So third derivative gives me lambda cubed minus 3 lambda squared minus 10 lambda. I'm going to set that equal to 0. I'm going to find the roots. So what's the first thing I can do here? Factor. Help me out. Factor out lambda, beautiful. Do not divide by lambda because then you just lost some key information. So all factors stay in the factory. Anybody see how this rolls? Set these up nice. So what do we got here? I'm sorry, what was it?
Lambda minus 2 plus 5. No, it would have to be plus 2 minus 5.
Plus 2 minus 5. I think, Grace, you were saying that, right? Something like that. I thought you'd said that.
I just knew 5 and 2. I didn't know the signs.
That's cool, yeah. But so like, 5 and 2, you can get 3 out of those if you add them in the right way. So just toss it in and then adjust the negatives and positives to match the inner term. And then this is equal to 0, so I've got lambda equals 0. Lambda equals, I won't need lambda equals 0, 5, or negative 2. Each one of those corresponds to a solution of the form e to the lambda t. So, notice that these are distinct roots. Today we're going to deal with the repeated roots in other cases. We'll have everything knocked out by the end of the day. But these are distinct roots. In other words, they're all different. When that's the case, what I'm doing right here, associating each one with the power of e, is exactly what you should do. So this one here corresponds to e to the 0t. And I'm going to slap a c1 in front of it. Then the next one is c2 e to the 5t. And then c3 e to the negative 2t. What's e to the 0t? 1. So this is just a constant. So I'm going to simplify this because this is 1. My solution, my general solution is x of t equals c1, a constant just by itself, plus c2 e to the 5t plus c3 e to the negative 2t. So no matter what c1, c2, and c3 are, if I take the third derivative minus the second derivative minus the 10 times the first derivative, whatever, if I do that to it, it gets 0. It all cancels out. Is anybody not sure what we just did? It's important to know what this means and what we just did. I'm going to trust you on that. So this is step 1, find the general. And then if you've got initial conditions, you're going to use these to find the specific constants that satisfy those initial conditions. So then the next step is, we'll come back to this chap in a minute. So now find, so step 2, oh God, I don't know, I guess this is 2. So 2 is translate roots to solutions. And then step 3 is find constants if initial conditions. What that means is that I'm going to have to take this and find those two derivatives there. So x of 0 equals 0. First off, actually, I would probably recommend crank out as many derivatives as needed. So that says crank out needed derivatives. So we have to go up to the second, so we have x dot equals 0. Do not absorb. So one thing here, don't absorb into the constants in this process right here, because you'll just lose everything if you do. But this is going to be 0 plus 5c2 e to the 5t minus 2c3 e to the negative 2t. X double dot is the derivative of that. So that's going to be 25c2 e to the 5t plus 4c3 e to the negative 2t. Okay, let me just check. Is everybody cool with me? It's been a weird weekend with the chime change. Is everybody cool? Just let me know. Cool, all right. So now plug in the initial values. So this first one, x at 0 equals 1 means that this equation, when I put t equals 0 in, I'm going to get c1 plus c2 plus c3 equals 1. I'm just plugging that right in here. And then x dot at 0 equals 0 tells me 5c2 minus 2c3 equals 0. Just plug it in 0 again for t, and then x double dot at 0 equals negative 1 says that 25c2 plus 4c3 equals 1. Negative 1, excuse me, bless you. And then here comes the fun part now. Linear algebra time. Got to solve that system for however many things you've got. Luckily, we only got 3 here, and we've got some really sweet little pieces of information here. Check this out. These two by themselves actually constitute a full system, right? This has C2 and C3 in it. This has C2 and C3 in it. So I can just solve these two for C2 and C3, plug that into this top one, and have C1. So let's do that. Let's just do that real quick, because this is straightforward. There's like almost infinitely many ways to solve these things. But let's call this 1, 2, and 3. I like to, when I do these 2 and 3 together, I like to label them so that if I have to look back at what I've done, I have a hope of recovering my work. This says that C2 equals 2/5 C3. That's the route I go. I mean, there's like a bit, like I said, you could get these to cancel if you wanted, multiply this one by 5, and then subtract down. That's another way, but I'm gonna plug that into 3. So this is just 2 right here, and I'm gonna plug that into 3, and I've got 25 times 2/5 C3 plus 4C3 equals -1. And I'm glad I'm with people who like this kind of stuff, because this could be boring if you didn't. So we get C3 equals -1/14. That's ghastly. And then C2 is 2/5 of that. So that's going to be 7/30. Wait, what's 2/5? Take that times 2/5. So
1/35.
thank you. So that wasn't working for me, so I appreciate it, Chris. Thank you. And then I'm going to plug both of these into equation 1, and what I'm going to get from that is C1 equals 1 minus C2 minus C3, and you know, I at this point I do not give a flying fuck what that is. That is something.
It's the common denominator 70. That helps.
70. Oh yeah. Oh, all right, Chris.
I'm just.
No,
Pointing out a fact.
no, we're gonna do it, we wanna do it. No, I'm just kidding. So 70 plus 2, and then plus, that's 5 of those, right?
Yes.
Yeah, 5 of those, that's actually pretty good.
Yeah.
I told you it'd be okay, Chris. So C1 is equal to 77 70ths, how pretty, 11 tenths. And then you would summarize, write your final solution. Thus, or hence, wherefore now and hence forever, x is equal to 11 tenths. 11 tenths, that's it. Where's my original? Oh, then plus C2 is e to the 5t, so minus 1/35 e to the 5t. Yes, thank you. Minus 1/14 e to the 2t? Negative 2t, thank you. That's my final solution. And so if you took that and ran it through this, all that would work. Yep. I don't want to go through and check it. We could, but that just sounds painful. We're just gonna trust in the system. This stuff works. Let's do this other one together then. Did anybody else actually solve any of these over the weekend? Cool, why don't you do that one for me, please? No initial conditions. This one right here. What's up, Lavina? Okay. Okay. And luckily it's just the general solution, so you don't have to go through all this. Aha, you did have something, yes.
C1, I have 1/10.
1/10. Oh, let's see. Okay, well maybe I did it wrong, so let's check. So C1 is 1 minus C2 minus C3. Did you get the same thing for C2 and C3?
Yes.
Okay. So let's see, so then C1 is 1 plus a 35th plus a 14th. I'm checking with you, you tell me, because we're,
I did it differently, but
let me see, let me come see what you did.
I didn't do the videos wrong as well. I did it like this and then I just left it there and got these.
Interesting. Boy, to get 1/10 out of that, I don't. Did you do all this? Or was this, did like a program do that for you? Okay, I was like, you were really spending a lot of time writing these solutions out.
Yeah.
Well. That's what's weird is we agree on the other stuff. Did I get? Did you? And you used the same 3 equations? Okay. Yeah. Oh, but you have C1 plus C2 plus C3 equals 0, not 1. And did I have 0 or did I have 1? I had 1. So I think that's the problem. If my condition was 0, I definitely would get negative 1/10 because then I wouldn't have the 70 70ths. I would just have 7 70ths.
Okay.
Is that, yeah.
Okay, so we're both technically right.
Yes, in some way, yes. I was right for the problem I did, yes. You were right for your problem. Wow, sorry. It's very squeaky lid. Let me show you some stuff. Get going here. Some stuff you probably saw a long time ago about factoring polynomials, but may have forgotten. What's that, Chris?
These are my favorite ones.
Factoring.
Like these polynomials where you can like break them apart in a specific way.
Like, what's the way you're thinking?
That you take out, like I guess what would be a lambda squared, and then you can combine the two segments together and then break that apart. There's a negative in the middle of them.
Yeah. So you group the first two terms together, group second terms together. Yeah, that's great. That totally can work here. That's a straightforward way. I'm going to show you some other ways too. But I'll go ahead and do this a couple ways. So first I'll do it like Chris did. And as soon as you see like the same thing, as soon as you see that lambda plus 3 occur twice, you know you've rocked this. Yeah. Has everybody seen this method before? And then you can pull the lambda plus 3 out. And so it's lambda plus 3 times lambda squared minus 4 equals 0, because that times that. It's that times that. And so that's a lovely way to do it. And then here you got plus or minus 2. Right? So we've got lambda equals minus 3 minus 2 plus 2 to write them in order, I guess. Anybody else do this a different way? You did, Labina? What'd you do?
So I found a value for lambda for which this whole thing was 0, and then I did like lambda, well it was 2, so it's lambda minus 2, and I did that 3 times, and I just added it bits and pieces so that I got the full form, and then it's kinda,
So you took a guess at what one of the roots was?
yeah.
Oh wow, okay. Yeah. And that's possible. That's totally possible. Let's talk about that. That is kind of what I want to talk about, that approach. Did you synthetic division?
I don't know names.
Okay. Let's talk about this. What I would do, oh shit, well I just erased it. Well, we have it encoded right there, so we know how to encode and decode that.
I just remember learning about changing that value now for sure.
Okay. Polynomial factoring tips 101, part 1. If you have a polynomial and you've got this leading coefficient, so you've got some lead on it, and then you've got like, we'll just use lambda at the end, and then you've got this constant at the end. If you don't have a constant at the end, when you've got things in power, you should be factoring out enough powers to get that to be a constant. So, for example, if I had this, I would first pull out lambda to the 6th and have that. So once you can get anything down to this point if you factor out the powers of lambda if we're needed. But one of the laws is that any possible root, if this thing has real roots that are rational, so all rational roots, this doesn't cover like square roots of 2s and square roots of 3s and stuff like that, but all rational roots are all rational roots come from this set. And the set is this: all factors, plus or minus all factors of the constant over all factors of the lead. So here we've got a leading coefficient of 1. That makes life really sweet. It tells me that any possible rational root has to be a factor of 12, plus or minus. So here we've got plus or minus 12 over a leading coefficient of 1, which is out in front here. Plus or minus, sorry, 1, 2, 3, 4, 6, 12. Like that. So in other words, one of these possible 24 things. There's 24 possible roots there that we could have if we have rational roots. Then what you do is you start testing them. Actually, here's a couple other things. Do you remember the sign change rule? Anybody remember that? Let's talk about that. So notice when I look at this polynomial, I can count the sign changes. So plus to plus, that's not So here's the sign changes, 1. So I only had one sign change in its natural form. I think this is Demov's rule of signs or something like that. One sign change, that tells me there's one positive root. And that turned out to be true. Then I go through and I replace every variable with the negative. So if it's an odd power, I make it a negative. So here I'm gonna let lambda go to negative lambda, and when I do that, I get negative lambda cubed plus 3 lambda squared plus 4 lambda minus 12 equals 0. So I'm just changing the odd powers to flipping their sign. How many sign changes do I have here? 1, 2. So I've got 2 sign changes there. So 2 sign changes in the lambda goes to negative lambda version. So that's the number of negative roots that I have. So I have 2 possible negative roots, or I also have 0. So like, if this had turned out to be 3, the possibilities would have been 3 or 1. Your possibilities get subtracted by 2 because roots generally come in pairs in a certain way. Sorry, I'm kind of saying this pretty sloppily. So this 2 sign changes in this one, this means 2 or 0 negative roots. Turns out I do have 2 of them. You might say to yourself, well wait, what if you had 1 positive root and 0 negative roots? What would that mean? That would be a complex pair of roots. So there's a possibility that you have a complex roots, and those always come in conjugate pairs, like this. So that's why we subtract down by 2. So I know there's 1 positive root. Once I find it, I'm good to go. Let's see, what else can we do here? Let's talk about synthetic division then. Then you come in and you start testing shit. Now I know you can do all this on a computer, like way faster, but it's so much cooler to know this stuff on your own, like you'll need to on an exam or something. So we'll get lots of practice with this. So synthetic division. So has anybody seen this before? Chris, yeah, maybe?
A long time ago.
Long freaking time ago, yeah.
One or two.
And you might have seen it, just not with that, the names, right? The names, we'll find out. So what you do is you write your coefficients across in a row. And essentially what you're doing is evaluating the polynomial at various numbers to determine if they're a root. Is this, yeah, starting to ring a bell, just like this little setup? Yeah, that you look like you're smelling something bad.
I didn't understand it way back when.
Okay, well, let's talk about it. Let's talk about it. So let's say I tried 1. So when I plug in 1, here's how it rolls. You initialize by bringing down that first coefficient. This always comes straight down. Then take the thing in the box. This is what I'm testing. Is that a root? Take 1 times 1, write it up here. Add down. Take 1 times 4. Write it here. Add down. Take 1 times 0. 0. Add down, negative 12. This is actually, so what is coming out here? What is this? It's this polynomial evaluated at 1. It's literally the same thing you would get if you went over here and replaced lambda with 1. Look what you get. You get 1 plus 3 is 4, minus 4 cancels, negative 12. So this is a way to evaluate that polynomial at various things. Let's try another one. So that didn't work. What I want here is 0. I want a 0 here because then that tells me that this polynomial at some value is 0, and that means it's a root. Let's talk about this again too. Fundamental theorem of algebra. If I have a polynomial and a root, and this is true, then that thing is a factor. That is one of the factors of the polynomial. That's what this whole method is about. So 1 didn't work, and I got negative 12. Let's try, oh gosh, 2. Because I know 2 is gonna work, right? I think, wasn't 2, yep. 2 should work, so let's see that. So write the coefficients. Bring down the leading coefficient, 1 times 2, add, 10, add, done. So first off, it's a freaking cool way to evaluate polynomials, but it's also like just a fun process to do. So I got 0 here, so this means 1 or 2 is a root. Awesome. Now here's my new polynomial. If I take that polynomial and I divide it by lambda minus 2, this is the polynomial I get. In other words, let me just point out to you what I have now. Lambda minus 2 is one of the factors. Here's what's left afterwards. See? Lambda squared plus 5 lambda plus 6. Now I've just factored that thing. But I'm going to do synthetic division to this piece now. I know there's only one positive root, so I'm done with that. So now I'm going to try another one. Let's try negative 1. So I start negative 1, 1, negative 1, 4, negative 4, 2. That's not a root. Let's try negative 2, which we do know is a root. And so you kind of play this game. There's some other ways we could narrow this down. I hope this is a root. Sure is. Here's the polynomial I got left. So check out what I've got so far. Positive 2 is a root, negative 2 was a root, and now I'm left with lambda plus 3. Right there. So there's my factorization. We'll do a bunch of these as we go through, but that's kind of cool. That is not bad. Synthetic division always kind of got me boiling.
When I first learned it, they just had so many lines. It was
This
like
is
a
the first
budget grid for everything.
Oh
Yeah.
God.
And I
Really?
didn't
Yeah.
This is the first time I actually understood what's going on.
I'm so glad. It's pretty simple. I don't know why they would make it hard.
I had no idea what's going on in synthetic division back then.
But now you're all over it.
It's more multiplication than it is division.
Literally.
It's yes, yeah. Well, let me show you how cool. Let me show you what you're actually doing. Watch this. If you put lambda in here, watch what happens. This is so cool. This is going to give you this incredible insight, I think. Since you're already like rocking some insights on this. I put lambda in here. Always initialize 1 times lambda. So you get lambda squared plus 3 lambda minus 4. Add down, what did I end up with? The original polynomial. So that's what I mean. You're just literally, it's a quick way to do this on the fly. Awesome. So we got our 3 roots. They're these. They are not repeated. So we are happy as can be, and we just write our solution out. X of t equals c1 e to the negative 3t, c2 e to the negative 2t, c3 e to the 2t. Done. Distinct roots is a sweet case. They're all sweet cases, but they're all a little different. Let's look at one where we have repeated roots. Today we're doing repeated roots and complex roots, and we'll have everything we need. So, repeated root case. And instead of going through this in kind of a minutia that I don't think is going to be helpful, I'm going to motivate to you why we're going to do what we're going to do. So, let's suppose our characteristic polynomial is lambda minus 3 squared. What is the equation that came from? Can you just reverse engineer this really quickly for me? What's the differential equation that represents? It's a good little back and forth here. You can put a 0 here if you want. What differential equation did that come from? You'll have to multiply it out, right? FOIL and shit. would you end up with that? What Diffie cube would do that for you? Kyle's got some. Take a look. Kyle's got. Oh, you're just, okay, you still can, okay, cool. Yeah, that's beautiful. Okay, Olivia's got it. Each power of lambda is a level of differentiation, right? So this is second derivative. You can, if you want to go, let's be crazy, do y's. Olivia did x's because we've been doing that. That's totally cool. Let's do y's and x's just to shake it up. There's our differential equation. And we actually know a lot about the roots already, right? We know the roots, 3 with a multiplicity of 2. So notice here that lambda equals 3, 3. So you would say here multiplicity 2. So what's one solution? What do you think one solution what should it be if all this is going to make sense?
3 or 0.
So Bob?
3 or 0. What do you want?
3 over 0.
No, just either 3 or 0.
Oh, either 3 or 0. Oh, yeah, but so like in terms of this guy here, Nathan, what like e to what power? I guess that's what I'm thinking about. So if we have lambda equals 3, what e power does that correspond to? E to the 3x. That's what I'm looking at there. I think you're confused by what I'm asking. Let's talk. Or think for a second. Maybe you didn't understand my question, and if you didn't, I'm sure others didn't. Right, this is just what we were doing. We take the root, got lambda not's a root, just put it up here, right? But I'm using x's instead of t's right now. So I can tell you're not getting this here, Nathan. So like, if lambda equals 3, just go back to where we were before. You would have said e to the 3t is a solution. Yeah, does that make sense? So that's all I'm saying here, that I got at least one of those. Does that feel a little better? Okay, cool. Good, good. So this is probably a solution. Let's actually check. Let's just say, suppose y equals that. Let's just make sure it works. So let's see here. So y prime is 3e to the 3x. Y double prime is 9e to the 3x. When I plug that in, I'm going to get, so let's see, y double prime minus 6y prime plus 9y equals 9 of those, minus 6 of these, so minus 18 of those, plus 9 of the original. And notice that those all cancel, and I do get a solution there. So this is definitely a solution. But we want as many solutions as the order of our equation. This is just incomplete. So what I want to tell you right now is that the second solution is this one. So we take that first one, but then the second solution corresponding to one of the next multiplicities is going to be x e to the 3x. We'll take this further, so let me prove that to you. So here's the second solution, let's prove it. Let's take y prime equals product rule, and then y double prime, yeah, and then 3x plus 9x. So I'm just product ruling like crazy there. Then let's see, we're gonna take this minus 6 of these plus 9 of those. So let's try that. So here's, I'll write out, this guy's just writing like normal, so I'm gonna put negative 6y prime underneath, and that's gonna be negative 6e to the 3x minus 18x e to the 3x. So I'm just multiplying this by negative 6, and then I'm gonna multiply 9 times the original, And let me know, when I add all that stuff together on the right side, does it cancel? I mean, I sure hope the hell it doesn't, because I'm just gonna walk out of the room if this doesn't work. I should call it. Let's see. I'm getting scared. Okay, so we have 6e to the 3x minus 6e to the 3x dead, so all the e to the 3x's die. 9 of these minus 18, that's negative 9 plus, add all up to 0. Do I need to explain what I'm doing? Let me stop for a second. Let's make sure everyone's in the car. Chris.
How do you get the second solution of, where did the x come from?
So that's the part that I'm not gonna prove that. I'm gonna motivate to you that when we have repeated roots, we get the next solutions by tacking on x's in front.
Got it.
So I just did that.
Yeah, no, okay, that's fine.
Yeah, that wasn't derived or anything. I pulled that out of a hat.
We'll spare each other the time then.
Yes.
I just wanna know, why do we need a different second solution? Is it just for funsies, or will we learn more about that later?
No, it's just that right now we don't have the full gamut of solutions. So Kendra, we have a second order equation here, right? What if I gave you some initial conditions? Y at 0 is 1, y prime at 0 equals 2. Right now, we can't handle that, because if we just stuck with this, let's do the general form, right? C1 e to the 3x. I can't make that work for both of those. So I've got to have that second solution in there to get the full set. Does that make sense? Yeah? Okay, cool. Good. Other questions? Vivian, I felt like you had one maybe.
It's not really relevant, but, so if we have two double roots, it would be one, I guess one root would have, or two roots would have x or.
Yes, exactly, yeah. We'll look at a bunch of cases, that's a good question. Any other questions on this? We're gonna do more problems together on this right now. Okay, so anytime you get a repeated root, you just keep adding powers of x to cover the higher multiplicities. So for example, if I had, let's say I had this equation. Let's go back to x for the hell of it. Third derivative of x minus 3x second derivative plus 3x first derivative minus x equals 0. So, characteristic polynomial. Like that. I hope I did this. Yeah, this has got to be right. Yeah, it's got to be right. Can't really play the game where we do the factoring, right? Where you group the first two and group the second two together. Doesn't seem to be working, even though I'm a little shocked that it doesn't. Let's do some let's do some synthetic division. So if there's rational roots, what do they have to look like based on what we talked about today? Think leading coefficient and constant term. All the factors of this over all the factors of the number out in front here. What do I got? 1 or minus 1, right? Literally, the only rational roots of this can be plus or minus 1. So rational roots, plus or minus 1. So let's do some synthetic stuff. We've got 1, negative 3, 3, negative 1. I'm going to try the positive one first. So I initialize, bring down the 1. 1 times 1 is negative, is 1. Add, you get negative 2. Put those together. Multiply that times that. Bring that up here. Add down that times that up there. Ooh, we got a root. 1 is a root. What are the possible roots of this polynomial? Lambda squared minus 2 lambda plus 1. So you just kind of keep synthesizing your way down to something simple. What are the possible roots of that?
Still 1 or negative 1.
Still plus or minus 1, right? It's all the factors of 1 over the factors of 1 with pluses or minuses. Let's try 1 again. Ooh, and I can even go here. Let's see, sign change. There's a sign change. So I either have 2 positive roots or 0 positive roots from Demov's rule. I'll write this out in case you want to look it up. Demov's rule of signs. Or is it Descartes? I think it's Descartes. I knew it was Day something. Descartes' rule of signs. That's it. It's been ages. So bring down the 1, 1 times 1, add that times that. Cool. I've got the second root. And now I can see here, look, this is just lambda minus 1. So lambda equals 1 is the next root. If you don't believe me, hell, let's put it in the little pocket. Initialize 1 times 1. Yay, I'm done. So this thing factors as lambda minus 1 cubed. And that means I have 1 with multiplicity 3. And so that means I have 3 solutions. What's the basic one? What's the e that's going to be involved in these? E to the what? E to the x. Yeah. Go back to your original form. Oh, I guess t here. Yeah. Just got to be careful. So e to the t corresponds to one of them. The second one is going to be what? Yeah, exactly. T to the t. And then what's the next one? T squared, e to the t. And put c's in front of that. So c one of those, c2 of those, c3 of those. Notice this is a beautiful polynomial that's just times e to the t. This is c1 plus c2t plus c3t squared e to the t. Isn't that pretty? Or, it's something. Everybody's got different mathematical lusts and things that feel right to you. So that felt okay. All right. Let me give you one to try. Okay, I got one for you. All right, let's see. Okay, hold on. I'm doing this on my head. Okay. Well, we'll see. Fourth derivative of y. Okay, hold on. Okay. Minus 5 times the second derivative of y. I guess double prime, what the hell? And then minus 4y equals 0. Can you please find the general solution for me?
Is that double prime?
Oh shit, this one isn't, don't go ahead and do that one. It's not gonna be that great. It's actually not a repeated root one, and it is a double prime, sir, yes, to answer your question. Do that one, but then here's the one I really want. Oh, that gives me plenty of time to run to the restroom. Awesome, thanks, Grip. on this one, are those the roots? Plus minus 1, plus minus 2? I'll kind of show you some neat ways to maybe do this one. On this first one, if you can catch that this is a quadratic in lambda squared, like if you can notice that, you can get this beautiful factorization out and then get the plus or minus 2, plus or minus 1 right out of that. That's kind of how, I mean, this is how I did it when I was doing my little cheat over here. I did this guy and worked my way back up. You could also use synthetic division, but be really careful. You would want to use 0 placeholders if you were doing that. So if I was doing synthetic division, testing possible roots of which there aren't all that many, right? Plus or minus 2, plus or minus 1, or plus or minus 4. Those are your only possible roots on that thing. So here, if you got those roots, and we can talk about all this, but your solution here is C1 e to the 2t, e to the negative 2t, e to the t, e to the negative t. And then you really hope you don't have a bunch of initial conditions, right? Nothing too messy because you get this crazy 4x4 system. Yes, Chris? Did I do something wrong? Yeah?
Wouldn't that give you positive 4? Because it's a negative 4 and negative 1.
Is that what happened? Did I?
Is
No,
this-
no, oh, it should be plus 4, shit.
Should
Yes,
the
thank
question be
you.
plus 4 or should
Yeah, I don't, okay, hold on, did you get complex roots on that? What the fuck happened?
I
It
stopped
was
solving
pretty
it after
bad.
I saw that.
I got the right numbers, but the signs didn't work and I.
Okay, let's just put a plus there, that's what I really meant. Thanks, Chris.
Yeah.
Yes, sir, thank you. So much for my secret machinations. This is what I really meant, thank you. God, what was it before? Let's see. So you would do lambda squared equals 5 plus or minus square root of b squared minus 4. Oh, it wasn't too bad, but it wasn't good either. It wasn't good. So you would have plus, what was it before, 16? Yeah, 40, square root of 41. Sorry about that. What about this one? You can kind of use the same trick here on that one. What did you get for roots? Anybody got roots on that yet? The good news is there's not many options for rational roots. So. And remember, you should get as many roots as the degree of the polynomial. So that's a key thing to keep in mind. Kitra, you asked a question earlier about why did we want 2 solutions instead of just 1? Think about in linear algebra, when you have a vector space of a certain dimension, what we're trying to do is find, in some ways, a basis for this solution space. And it's n-dimensional, so we need n independent vectors, and the vectors are functions here. So it's kind of like that?
Mhm.
Yeah?
Yeah.
Yeah, okay. looking good here? Yeah, is this making sense? Are you good, Labina?
Yeah.
Okay, cool. Am I good? Am I doing all right? Okay. Yeah, all right, yeah. Beautiful. Can I answer any questions about any of this or any questions that are arising at all? Do you see how I'm treating this just like a normal quadratic? Like I saw that this could just be factored like this. Just like you either see those things or you don't, right? But even if you hadn't, you could have done synthetic division on that. 1, 0, -2, 0, 1. And you have two possible roots, 1 or -1. Those are the only possible rational roots you can have here. And so you could easily narrow it down that way. Okay, let's do one last one. What about this one? This is a fun one. What if I told you that the fifth derivative of y was 0? And I asked you to solve that differential equation. What's the characteristic polynomial? That's good. Raised eyebrows, good. Yes, that's right. Your eyebrows are raised appropriately. What's my polynomial here? Tell me.
Lambda to the fifth is equal to 0.
Yeah. What's the solution? Yeah, of multiplicity 5. So I've got 5 zeros, so lambda equals 0, 2, 3, 4, 5. So when you have 0, realize you've got this as your base e. That's just a 1, right? That's just a 1. So my solutions are e to the 0t, or x, sorry, we're using x's here, x e to the 0x, x squared e to the 0x, x cubed e to the 0x, and then one more, x to the fourth e to the 0x. I wouldn't write those e to the zeros, those are just 1. So what are my solutions? 1, x squared, x cubed, and x to the fourth. So just a fourth degree polynomial will satisfy that. So here we have y equals c1 plus c2x, c3x squared, c4 x cubed, plus c5 x to the fifth. Wait, did I get, oh no, wait, x to the fourth, shit, yeah, there we go, cool, didn't copy that down right. What happens if you take the derivative of a polynomial in fourth degree 5 times? Get 0. That's all this is saying. So when you have lambda equals 0, so 0 roots are polynomials. That's where polynomials come from in our solutions. All right, we got one last thing to get through, and that is complex roots. This is a little bit involved because I got to tell you a story that you may or may not have heard. I don't know, but I'm going to tell it to you anyway, and we'll see how it goes, see how you feel about it. Definitely need a really nice pen for this story. That's a good pen. So now let's do complex roots. So we've got distinct roots, repeated roots, and this is the only other possibility left. Complex roots. So for example, I had something like this. You know, I have like lambda squared plus 1 equals 0. Then here lambda equals plus or minus I, where I is the square root of -1. That should be somewhat familiar to you from your math life somewhere along the way. You might not have done it recently, but it should not surprise you that there is an imaginary number called I. I hope not. If so, we'll have to have some long heart-to-hearts, and I'll happily talk to you about it, but we should talk about it. I want to derive a formula for you. is the Taylor series expansion of e to the x? Do the eye thing. Do the eye thing with the cheeks at the same time. Anybody know this off the top of their head? Yeah, mathematicians, we should know this, huh? It's 1 plus x squared over 2 factorial x. It's so beautiful that, and such an astounding rhythm that now you'll know it forever. Especially I made such a big fucking deal about it, right? It's like, oh God, I better remember it, I guess. But it makes a lot of sense. What is the expansion for sine? Now, if we didn't know this one, we might not know that one. But I never know. It's also quite lovely. How could I use this series right here to get this series? How could I use this and calculus to get that? Yeah, take the derivative, right? Derivative of sine is cosine, so let's take the derivative of this series. X goes to 1. X cubed goes to 3x squared. The 3 cancels with the 3 in the factorial in the bottom, right? So let me just write this first one out. And that leaves me with 2 factorial in the bottom. Plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial. And once again, we see just gorgeous rhythms. Okay, so we need these. Because what I'm going to do is mess with I. And let's talk about I for a second. I squared is -1. That's kind of like the heart of the definition of I. It's a number whose square is a negative number. What's I cubed? Negative I? It's I squared times I, right? So it's negative I. What's I to the 4th? 1. What's I to the 5th? Square root of -1, or just I? Yeah, exactly. We're back to I again. And then I to the 6th is I squared, so -1. And we've got this beautiful cycling.
Isn't it every 4?
Every 4, absolutely, yeah. So we've got this beautiful cyclic nature in the powers of I. Makes a person think there's gotta be some trig in there. Seems like there ought to be. And sure enough, there will be. Because what we're gonna do is we're gonna take this formula and we're gonna replace x with ix. So I'm going to replace this x here with ix, and so every occurrence of it, so in other words, e to the ix is equal to 1 plus ix plus ix squared plus ix cubed plus ix fourthed on down the way. All I'm doing is taking the Taylor series, replacing x with ix, where I is the square root of -1. And then I'm going to simplify. I squared is -1. I cubed is -I. I to the 4th is 1 again, and I've got that whole rhythm over there. So this turns into 1 plus ix minus x squared over 2 factorial. So notice how that just becomes -1. This becomes -I. And then I'm back to just the 4th power, so it's just good old x to the 4th plus 4 factorial. And then what would come next? I to the 5th is just back to I. And then minus x to the 6th over 6 factorial minus I x to the 7th over 7 factorial. Back again to x to the 8th over 8 factorial. And then it'll stay plus a couple, it goes plus a couple times, then minus a couple times. So on and so forth. Now I'm going to group together the real part and the imaginary part. Notice how every other term has an I in front of it and every other doesn't. So let's put all the doesn'ts together. That's the real stuff. And then the rest of this stuff has an I in front of it. I'm just going to pull that out in front. So I've got IX minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus plus happily forever, evermore. Can somebody tell me what I just wrote?
Cosine plus I sine.
This is cosine of x plus I sine of x. So in other words, what we know, and you've probably seen this before, but it really never fails to amaze me, is that e to the ix is actually the same thing as cosine x plus I sine x. Yes indeed. And then, so this is a pure imaginary exponent. Complex numbers actually come in like this. So what if I had e to the alpha plus I beta? So that's a full complex number up there. Real part, imaginary part. Well, I would use the properties of exponents to do that. And then this is actually called Euler's identity. Because what did Euler do? I forget everything. So this is e to the alpha times cos beta plus I sine beta. Let's just leave that at that for the time being. All right, so now that's enough to get us rolling. So now suppose our characteristic polynomial had alpha plus or minus I beta as roots. And one thing I want to point out is when I have a polynomial with real coefficients, these always come in these conjugate pairs. So those are conjugate pairs. They always come 2 at a time. So if I had these as roots, we'd have solutions e to the alpha plus I beta t and e to the alpha minus I beta t as solutions. Or, x if you're doing a yx. So we're still playing that same game. I'm just taking the roots, slapping them as an exponent on e, and saying, oh, that seems to be working so far. So that means we'd have C1 e to the alpha plus I beta t plus C2 e to the alpha minus I beta t as our solutions, or as a general solution. So that's the general form. Let's play with this. Let's now take this and rewrite it like I did at the top. So this is equal to C1 e to the alpha t times cosine of beta plus I sine of beta t, beta t. Cosine of beta t plus I sine of beta t. Plus C2, do the same thing here, except we got negative I beta. So we just got to be careful with that. So I got C2 e to the alpha t cos negative beta t plus I sine negative beta t. Cool, we're almost done. We've almost done a very painful thing that luckily we won't have to do again. Does that, let me know if this is making sense. Or if I can clarify anything. No? Okay, cool. So, stuff here can be grouped. Oh, how could I rewrite this? What can I do with this? Can I rewrite either of those using odd and even properties? Is cosine even or odd? These are
Odd.
no.
Well, then it's even.
Yes, correct. So even means you're symmetric around the y-axis. Cosine is even. So if you replace the argument with a negative, it just absorbs, it doesn't matter. So cosine of negative something is the same thing as cosine of that same something, right? Because it's symmetric like that. So this cosine of negative b, I can rewrite that as cosine of beta t. What about sine? What is sine? So, Chris, now what? Tell me what you said before.
Oh my gosh. Let's say odd.
Yes, good call. Sine is odd, so this is, you can pull the negative out in front.
Right.
You can pull the negative out, negative gets absorbed. Now I've got a bunch of stuff that's starting to look very, very similar. First off, notice that every single thing here has an e to the alpha t on it, right? Every single thing here. So that's cool. And then I've got this cosine of beta t here and this cosine of beta t here, and that's going to be c1 plus c2 cosine of beta t. That's just the algebra, that times that plus that times that. And I've already got the e out in front. But then I've also got this sine stuff, so this is going to be a little bit weird, but not too weird. Notice I have I sine, and then here this is I sine. So I've got I times c1 minus c2, because of that minus we pulled out, sine of beta t. Almost done. These are just constants. And I'm going to call this d2, and I'm going to call this d1. And because this is a plus here and a minus here, I can always make d1 and d2 whatever I want by picking c1 and c2 to be whatever I want. So look at what I've got here as my final solution. I've got e to the alpha t times d1 cosine of beta t plus d2 sine of beta t. I'm hiding all the imaginary stuff. It's totally cool. It all works. But we can think of this as we actually have two solutions. So e to the alpha t cos beta t and e to the alpha t sine beta t. These are the roots that correspond to an alpha plus or minus I beta root. So if you see a complex root, you get those two solutions automatically. That would, just give me one more minute, just one more minute, please. Promise. I just want to do an example really quick. And then we'll be done. And then when we come in Wednesday, we're just going to work a crazy amount of problems, and I might push it just a tiny bit more. But you now understand how to solve any homogeneous nth order differential equation with constant coefficients. You're set. Putting all these things together. So here's one last example. Let's say I've got a mass spring system. Undamped mass spring system. Yay! I don't know what, so K is 4, M is 1. Whatever that means. Got a mass spring system. So what's my characteristic polynomial? Lambda squared plus 4 equals 0. Get the roots. Maybe you don't see them right off the bat, so use the quadratic formula. B here is 0. B squared is 0. Minus 4 times 1 times 4 over 2. So lambda equals plus or minus square root of negative 16 halves equals plus or minus 4i halves equals plus or minus 2i. Those are my roots of that. Plus or minus 2i. So my solutions, look at how, I'll put this up here. This corresponds to e to the alpha t cos beta t and e to the alpha t sine beta t. What's my alpha here? What is alpha for this? What number's in front? 0. 0.
Oh yeah.
Yeah. Does that make sense? Yeah. Okay, cool. So I'm gonna have e to the 0t cosine. Beta is what? 2. Cosine of 2t. E to the 0t sine of 2t. In other words, just sine and cosine of 2t. This is dead, right? So my general solution and that better be my general solution. This spring had better have harmonic motion. And it does. So the complex roots give you harmonic motion. We got more to talk about on Wednesday. But man, you got a lot. You can do this. Yes, ma'am.
So why would alpha be 0?
Because if I have a pure imaginary, like 2i, there's this unspoken secret 0 in front. So just think pure imaginary, there's no e on there. It's just a pure cosine or a sine.
So why would it not be pure?
When it would not be pure is if I had had like something else in here. So like when I did this, that's a great question. Think about when it would not be pure. It's when something appears out here to give me that real part. So, but when that b is 0, you got like, yeah, good question. Yay, all right, we're gonna come back and just kick butt with this stuff on Wednesday. You have a new web work. You should be able to do actually a lot of it. You can probably do everything now, but it might take some pushing.
Did you
Yes.
guys write your own blurbs?
Yes.
Okay.
Why?
I figured. I could just read it and I was like, this sounds like them.
Does it? Like
just
it
makes
sounds like
sense.
each person who wrote it?
Yeah, it does. Because you use a lot of the strange number for the square root or same magical properties.
Yeah.
And then hear a lot of like application and practical.
It
It's like, it just sounds
Yes.
like each of you guys. I think it's fun.
Yeah, we do write those blurbs, yeah.
Do you hear it?
Abstract algebra is the study of abstract mathematical structure.
We might have a. I just thought it was funny.
You, oh yeah, you guys, yeah.
I have a list so much like.
You can have a brand new, if you want to. Alright.
Thank you, Dr. G.
Thank you.
Also, all paying prepared.
Set up, yeah, we should advise. I'll like send out some emails, we'll figure it all out.
You could like.
Are you like usually free before this class, if you have a class before this class?
I have an hour.
Like, you.
Okay, before this class, that'd be great. Cause I'll be in there, so honestly, anytime you want to come in, you can just. Yeah, that'd be great too. We hung the doors. Thank you.
So lovely.
Pat is very much like, so this is what this class is.
Like,
We
yes,
are,
that is.
we are like totally like orthogonal human beings.
Yeah. It
Yeah.
works though. It's fun to have both of you guys with us.
It's
Yeah,
good.
Then you get the variety.
You do, yeah, definitely. You couldn't take, I don't know, you couldn't take too much of either, just only that,
That's
I would
fair,
think,
yeah.
yeah.
It's gonna be weird not having a class. Like
It's,
this
I can't
next
believe
semester,
it.
though.
It's, well, you will actually be teaching with me.
Yeah, that's fair. I'll still like
So,
be in your classroom.
yeah, but not
It's
math.
not math, and that's gonna be hard. It's not? What are you doing?
It's
It's the freshman RCC. Oh, cool. Yeah, it's gonna
It's
be
my
so fun.
Yeah.
What's the class? What is it? Zen and
Zen Lab is the